Good morning, class. So before we go through the last lesson, Unit 3, Lesson 9, Family of Quadratics, we want to see a visual of what's going on. So recall that there are three different forms of the quadratic functions: the standard form, the factor form, and the vertex form. So what family of quadratic function is? Well, think of what makes a family. Usually there's some kind of common characteristic, some common feature between a family perhaps. And so for these families, for example, family number 1, if you look at the standard form, a key characteristic of the standard form is that you are told the y-intercept, right? And so this kind of family will have the same kind of y-intercept. And I've modeled an example where three clearly different looking parabolas have the same y-intercept of varying a values and b values. That's family number 1. Family number 2, when we work with the factored form, we have the same x-intercepts for this type of family. And if we have the same type of x-intercept, as a result, we also do have the same axis of symmetry based on what makes a parabola. And therefore, this parabola has x-intercepts 1, 0, and 5, 0, again with varying a values. And the only thing different between all these, this type of family, is that they have different a values. Family 3. So family 3 is based on the vertex form. They have the same vertex and therefore the same axis of symmetry, because what axis of symmetry is that it is the x of the vertex. And so this is going to make family number 3. So with that in mind, for families of quadratics, it's not really emphasized heavily for the Unit 3 summative, just to give you a heads up, but there are little ideas that might be helpful for future units. Number 1, sometimes the given problems may have many solutions only because not enough information was provided to make the solution unique. The many solutions that satisfy the given conditions are called a family of functions. Give a family of quadratics that share the same vertex and open down. So that means we're considering family 3. They have the same vertex and it is opening down. And so I need to give myself an example. So example given is that, okay, let's say I have the vertex 0, 1, and because it says my parabola is opening down, that means my a is negative. So if I work that out, and I should be working with my vertex form because I'm given the vertex, I am going to start putting values in. And when I put the 0 in for h and 1 for k, that equation simplifies to negative x squared plus 1. And then I have, let's say I give you a different a value. So I'm just trying different a values that are first negative 1 and second negative 0.5. And I'm noticing I get the standard form negative 0.5 x squared plus 1. So as you can tell, there are infinite many numbers of these type of equations where the vertex is 0, 1 and a is negative. So we want to be able to write it in a way that we can organize it. So to quote it all, I want to have y equals a. Well, because the a values are still varying, and I have my x minus 0 because the h is 0, and then squared plus 1 to represent that k is 1. And keep in mind, I do need to write some kind of barrier domain, not a domain, but a restriction on this equation by writing a is less than 0. So that is an example of a family of quadratics that shares the same vertex, let's say 0, 1, and it opens down. Number 2, find a family of functions that have zeros at negative 9 and 5. That means I'm dealing with family 2, okay? So they have the same zeros at negative 9 and 5. So again, I'm going to use the factored form in this case because I'm dealing with zeros. So I have y equals a, x plus 9, because I'm using the opposite sign because, again, there's already a negative within the equation of the factor form, and then bracket x minus 5. So I want to be clear on my a values. I'm going to write a elements of reals because a can be any real number. And meanwhile, I can't have a equal to 0 because that means that I will just have a horizontal line, right? If I have y equals 0, that's just a flat horizontal line. 2a. Give another condition that will ensure that his family of many quadratics is one unique parabola. So in order to make my parabola unique, I want to use a coordinate such as 6, 3 so that I could get a unique a value and therefore a unique parabola. And so I'm going to plug in 6, 3, and I just made that up. I just made up a single coordinate, and I'm going to plug it into my family equation. So this is going to, by giving another point on a quadratic equation to get a unique solution. 3 equals a bracket 6 plus 9 bracket 6 minus 5, which simplifies to 3 equals a bracket 15 bracket 1. And I will get 3 equals 15a. I'm not done yet. I need to simplify and get a by itself. And I'm going to do that by getting 3 equals 15a. I'm going to divide both sides by 15. And that will simplify to a equals 1 over 5. And therefore, I need to write my concluding unique parabola equation. So I have my a value of 1 over 5, and my x-intercepts are -9 and 5. Therefore, I get y equals 1 over 5 bracket x plus 9 bracket x minus 5. So I give him a unique example where I have a unique a value. Question 3. Number 3. Find a family of functions that have zeros at 2 plus square root 3 and 2 minus square root 3. Square root 3 is irrational portions because it cannot be represented as a fraction. I'm going to plug the zeros into the factored form, making sure that I include brackets on these expressions, like so. So I have the following. When I plug in the zeros into the factored form, I get that. I'm going to do one more step of simplifying the brackets within. And so I get x minus 2 minus square root 3, x minus 2 plus square root 3, where a can't equal to 0 because otherwise it is a horizontal line. And that is my family equation for part 3. Question part 3a. Find the unique equation of the family that passes the point 1, -5. So I'm going to rewrite that equation above. And so for my equation, I'm noticing that I could simplify some parts. And when I do that, I'm going to do FOIL, like so. And I will get, according to difference of squares, I will get it in the form of a squared minus b squared, because my x minus 2 will multiply to x minus 2 and it'll equal x minus 2 bracket squared. The parts in the middle will cancel out because one is a positive, one is the negative version of another. And then minus square root 3 times plus square root 3 is equal to minus square root 9. So that's what I get within the brackets. I'm going to simplify by expanding that x minus 2 bracket square out by foiling again. And I get this, and I need to collect the like terms. And now I have the equation y equals a bracket x squared minus 4x plus 1. Okay, that is the family of the equation, but now you have to make it so that it goes through the coordinate 1, -5. So I'm gonna now let it go through that coordinate. And so I'm gonna simply plug in 1 for x and -5 for y and try to solve for my a value. When I do that, I get the following for the first line. 5 equals a bracket, smaller bracket, 1 squared minus 4 times 1 plus 1, close the bracket. I'm going to get inside 5 equals a bracket 1 minus 4 plus 1. And so I get 5 equals a bracket negative 2. I'm going to divide both sides by negative 2. And so I'm going to get a is equal to negative 5 over 2 because I don't want the negative in the denominator. And so I get a is equal to negative 5 over 2. And finally, I have to write a concluding equation, the unique equation. And I get y equals negative 5 over 2, bracket x2 minus 4x plus 1. And because I just have a unique equation without any a values, because I solve for my a, I do not have to state the further restrictions. So that is my unique equation that goes through the above coordinate and goes to the point 1 comma negative 5. Question 4. What you have is a fancy way of saying that you have an input of 2 and an output of 0, meaning a coordinate of 2 comma 0, which is actually the x-intercept because the y value is 0. As well, you have a y-intercept of negative 3, which you can write in coordinate form as 0 comma negative 3. Initially, I'm going to write down my standard form and my factored form and write down all the given features within those equations. So these are my standard and factored form. So as you can see, I know that I have my c value within the standard form, and I know that I have one of my x-intercepts. So I'm going to work with that. So as my step number 2, I'm going to sub in some of the values that I know. So for example, within the factor form, I'm going to sub one of the x-intercept, which is t equals 2. So that is my original equation. But if I look around a bit, I notice that I also have another coordinate 0 comma negative 3. That means I could also plug that in. So I'm going to plug 0 comma negative 3, and this is what I get. Negative 3 equals a bracket 0 minus r, 0 minus 2. Let's simplify that. So that's equal to negative 3 equals a bracket negative r, well, and then times 0. So let's plug that coordinate in, 0 comma negative 3, and we get negative 3 equals a bracket 0 minus r and 0 minus 2, which should simplify, and I should be able to solve for a at this point because I should be able to solve for a at that point. And so this is my next line. I have negative 3 equals a bracket negative r negative 2. At this point, I'm going to get a by itself, even though I know there's a variable within involved. So I get negative 3 equals 2ar. I have to divide both sides by 2r. And I'm going to get a is equal to negative 3 divided by 2r. So a lot of steps here. So I'm going to summarize by writing my family, okay? So that is my step 4. Step 4, I have my family. Well, what do I have? I have this simplified expression for a, and then I have one of my x-intercepts. So I'm going to write down all I'm given. So that is my family function so far with everything that I have. So I'm going to call that the family equation, equation 0. No, it looks kind of complicated. So right now what we have is we have one x-intercept, and then we have it in a certain format for the a value. So in this kind of complicated example, all that means is that we have a situation Okay, so I know this looks a little more complicated from the previous, so I'm gonna start plugging in some very simple values, meaning, okay, let's make r equals to 1, because remember, they told me to give me 2 non-equivalent functions that satisfy the following, and as long as it satisfies the 2 conditions, I'm correct, right? And so I'm gonna sub in, I'm gonna give 2 possibilities, I'm going to choose r equals 1 just because that's a very simple number, and r equals 2. And when I do that for the first part, this is my equation that I get. So I'm making sure that it has an x-intercept of 2, and now I'm forcing it to have an x-intercept of 1, and I'm going to plug in that r value of 1, and that's my new a value that I get. And then for a second possibility, I just chose r equals 2, plug that into the family equation, and I get this. So now I have 2 equations, and all of this probably look like gibberish, and we need to see a visual of what's going on. All right, so if I look at my light blue family equation, all I have to make sure is that it has an x-intercept of 2, 0, and it goes through the y-intercept of -3. I don't know exactly what the r value is. It could go either way. My family equation, that's just really general. It's my attempt at showing it's being very general, okay? But it's the pink and purple that are the specific. If you look at the pink and purple, the pink graph does go through the x-intercept of 2, 0. Meanwhile, it does go through the y-intercept of -3. See how I've satisfied that? Look at the purple. It also goes through and has an x-intercept of 2, 0, but you also notice that it happens to be the vertex there and has a y-intercept of -3. So as long as I'm working with the information and trying to organize it into one of the equations and simplify it so that I have a family, as long as I can give 2 equations where it satisfies those 2 conditions, that should be okay. So that is what it looks like if you did it by hand. And then meanwhile, if I graph it, the actual representation looks like this. Just a cleaner look. And that's it for question 4. Different looking equations that give the same answer. This can happen when many frames of reference can be chosen, i.e. the x and y axes can be placed differently since the question doesn't specify where to place them. Note, these are not considered to be a family of functions since graphing them in the same frame of reference coordinate system will yield a different graph. Find 2 different equations using different frames of reference that can model the following. Okay, so what this means is for this suspension bridge example, and where you have 2 towers at the end, there might be different ways of looking at it. Where are you going to put the origin to be? So I have my red version and my green version. So my red version says that, well, let this be the origin. My green version says, well, let this part be the origin. So you can have a drawing of a graph, but you can put the axes differently. And in certain ways, it might make more sense in one way, and in certain ways in a different way. There's not really a wrong way, but it's just about perspective. So if I was to further expand on the red example, it helps to put the coordinates in. I'm noticing that the 2 towers are 80 meters apart. Well, if I moved over right by 80 meters, that's 80, 0. Meanwhile, well, if my 2 towers are 20 meters high and this is my 0, 0, that means this must be -20 because I've gone down -20 meters. Meanwhile, it says that the shortest vertical cable right here is 4 meters long. And so that means my vertex of this parabolic shape that this bridge creates is of the coordinate. Well, halfway through of 0 to 80 is 40. So that means my x value is 40 for the vertex. And my y value, well, my y value is, well, if there's a distance of 4 meters from -20 and to this point, well, this must be -16. And therefore, my vertex is 40 comma negative 16 if you look at it in the red version way. Meanwhile, the green version way is that, well, if this part is my origin, that means that the vertex for the green coordinate will be 0, 4. Is there any other significant coordinates? Maybe over here. Well, distance from there to there, well, you will have moved over 40. That's 40, comma, and you'll have moved up 20. So that's the coordinate. And all it's saying is that if you're looking at a parabola, if you're looking at a shape, depending on where you put the x and y axis, you might have a different kind of coordinates, but it's just all about perspective. All right, let's do it algebraically. So the red version. All right, so the red version has a vertex of 40, negative 16. Meanwhile, a known coordinate, I have a few. I have the 0, 0 and the 80, 0 that goes through the parabola like so. So I'm going to start plugging things in. So for the red version, I have the vertex formula. I'm going to plug in 40, negative 16, and I'm going to plug in 0, 0. And when I do that, I get the following. I'm going to simplify so that I get 0 equals a bracket negative 40 bracket squared minus 16. And I get 0 equals a bracket 1,600 minus 16. I have 16 equals 1,600 a. I'm going to divide both sides by 16. Oh, sorry, not 16, but 1,600. And then I'm going to get an a value of 1 over 100. And I'm going to put that all in. And for my green parabola, I get y equals 1 over 100, where my vertex is 40 and negative 16. So that is my red version. Notice my red version has an a of 1 over 100. Well, if you're looking at a perspective of the green version, what do you think will happen for the a value? Well, I'm dealing with the exact same parabola, right? And so my vertical stretch should be exactly the same. And let's see. So we have the same parabola, but different perspective. Okay, so we have for the green version, so I have y equals a bracket x minus h squared plus k. I'm going to plug in the coordinate 0, 4 and a single coordinate that goes through the green parabola. And I have the following. I plug in my h and k and x and y, and I get the following. So that part is going to simplify to 20 equals a times 40 squared plus 4. 40 squared is equal to 1,600. So I get 20 equals 1,600a plus 4. I'm going to move that minus 4 to the other side. And I get 16 over 6, 16 equals 1,600. I get 16 equals 1,600a. I want to divide both sides by 1,600. And I'll get a equals 1 over 100. And therefore, I'll get y equals 1 over 100, x minus 0, bracket squared, plus 4. So when we look at the big picture, what we're noticing is that basically we have the same a values because we're dealing with the same parabola, and it doesn't matter where you put the origin to be, my vertical stretch should be the same. Meanwhile, depending on how and where you put your x and y axis, you will get different vertex values because you're looking at it from a different perspective. Okay, part A. So if you look at the question, I basically need the supports to be 10 meters away from my bridge here and here. And they want me to check whether if having it as 12 meters is fine. So what I'm going to do is I'm going to write the red version. Well, for my red version, at this coordinate, well, if this is 10 meters apart, that means my x value is 10 because this is my origin. For the graph for the support over here, I have, well, if this is 10 meters apart, that means my other x value is 70. So I have an x value of 10 and I have an x value of 70. And I'm going to plug that in and see what y value I get. So I'm going to plug in those values into the equation and I get the following. I'm going to be able to simplify this equation to get the y value. I am getting a y value of negative 7. What does that mean? Well, if this is 10 comma negative 7, that means this is 7 meters, right? Well, the whole thing is actually 20 meters. And so that means that the tower standing here should be 13 meters. And same over here. So let's go to the green version. The green version will have x equals 30 and negative 30 because we have different perspectives. Let's take a look. So if I have my towers here, well, since this is the origin, I'm going 30 meters left, 30 meters right. So I have a value of negative 30 and positive 30. And so I'm going to plug that in, and I'm going to plug x equals 30 in this case, and I get y equals 30 exactly. So y equals 13. So although our coordinate looks different and the y values look different, what they're saying is exactly the same. And so having a y value of negative 7 in the red version case is telling you indirectly that the pole standing has to be 13 meters tall. For the green system, it is 13 meters long just because of how my axis has been written down. And so as a conclusion, I can say, well, you're dealing with the same thing if you're comparing it to the picture. We're dealing with the same thing. Doesn't matter which equation is used to answer questions in A and B. So not really, no, because we are really dealing with the same problem, just different perspective, but you just have to do one more step of understanding. Meaning in my green system, I was able to say right away that my pole standing is 13 meters tall. Whereas in the red system, I had to interpret it. Because you wouldn't think that this tower support is negative 7 meters, right? So I had to interpret what that meant. I had to turn it into a positive frame. I had to take difference. I had to really think about what was going on. And so when I look at B, you can probably assume that. So when I look at B, I'm going to just go ahead and look at the green version. Just because when I'm talking about the support, it's a lot easier if I look at the green version because that value I get directly represents all these possible supports that I can have to support this bridge. Okay, I'll use the green equation just because it makes a little more sense in this case. Well, what do you think I'm going to sub in for X or Y? Well, where should the 12-meter support pole be placed? Well, that is a Y value that they're telling you. Okay, so when I look back at the picture, well, we know that this is 13 meters for it to work out. So that means that somewhere along here, I need my 12-meter support. I'm going to do that one with you. So when I sub that 12 into my green version, so I get 12 equals 1 over 100, bracket, I don't know my x, minus 0 squared plus 4. I'm going to subtract both sides by 4 to get rid of the 4s. Oops, not that side. And I get 12 minus 4 is 8 equals 1 over 100 and x bracket squared. Notice that by BEDMAS backwards, I want to get my x by itself. First, I'm going to multiply both sides by 100. I'm multiplying by 1 over 100, the reciprocal of 1 over 100. That's going to get rid of the hundreds on the right side. I get 800 equals x squared. Final step. I'm going to take the square root of both sides, and I'll get x is equal to approximately 28.3 plus or minus. Well, look how where the order is for the green version. It does actually make sense. And so then I have to have a concluding statement. Therefore, place the support poles 28.3 meters away from the center. So both the right and the left side from where we're at. And in this case, positive and negative does make sense. Okay, question 6. Sometimes a given problem can have many very close approximate solutions. This occurs when dealing with raw real-life data because it is not possible to have perfect measurements, and real-life situations can fluctuate from many different variables. Again, these are not considered to be a family of functions since the approximate equations will yield slightly different results. Plot the given data as a scatter plot and create a quadratic line of best fit. Create a quadratic curve of best fit. So when I'm given, especially years, I need to try to interpret it to write it in terms of t. So I don't want to plug in 1994 for t, and it's not going to really make sense number-wise. So I'm noticing that the years are being gapped by 2 years. So let's say I set 1992 as t equals 0. So that makes 1994 t equals 2, and then 1996 4, etc., etc. I'm just going up. It's going to be a lot easier to organize your year by t values. Next, I wrote my title, which is always dependent versus independent format. I started plotting all of the values with my new t values, meaning, I organize it so that it was from 2 to 20. And notice that I have this part to show that there's actually years before that, but we're focusing on these years. So based on my plot, I'm noticing some important information such as, well, this looks like a potential vertex. Where is the vertex? Well, it's at 8, 50. Is there anything else? Well, we're not going to have a line of best fit, which is what we're familiar with from maybe grade 9. Instead, we have a curve or a parabola of best fit that we need to draw. So I'm going to draw it, and I'm going to try to connect as many coordinates as possible. That's how you draw a line of best fit or a parabola of best fit. You want to connect as many dots as possible. And notice that I am missing some of the coordinates, and that's okay. I don't want to draw it in a way that I'm trying to force to connect all the dots. Because if you notice, it doesn't look like a parabola anymore. Whereas the blue parabola does look like a parabola. So, question B, determine the approximate equation for your graph that will model the scenario. So it's always useful to think about what form do I want my equation to be in. Well, I don't want it in standard, but I notice that I have the vertex. So I'm going to use the vertex form. I have a vertex of 8, 50, and I'm going to start plugging things in. And I'm going to sub a single coordinate that is all my parabola best fit, and make sure that you're not using any coordinate, although that seems reasonable, but you're going to pick a coordinate. You're going to pick a coordinate where it touches the parabola best fit. In my case, I used the coordinate 2, 68, the first coordinate. When I do that, I will get 68 equals a, bracket 2 minus 8, bracket squared plus 50. 2 minus 8 simplifies to the following. 18 equals a, bracket negative 6, bracket squared. Negative 6 squared is equal to 36. I'm going to divide both sides by 36. And I get a equals a half. And when I get a equals a half, that means I could plug it back to my original equation, and I will get the following. And the following is my approximate vertex equation. Part C, use your equation to interpolate how many people will be over 100 years old Okay, so for 2007, see, you don't want to plug t equals 2007. That's going to be cause a big problem. And so I have to make sure I'm using my smaller t values. Notice that for 2007, it's a value between 2006 and 2008, which means I'm going to actually sub in the value t equals 15. What interpolate means is that you're working within the data. Within the data meaning I'm using the parabola of line of best fit, and I'm working within. That's what interpolate means. So I'm going to go ahead and do that. And when I do, I'm going to plug in t equals 15 into my equation. I get the following. I'm going to simplify that. And once you do that, you get 74.5. What does that mean? Well, my y value means number of people in thousands. So really 75 people where the numbers are in thousands. Again, 2012, well, that's extrapolating. Reason that is extrapolate just means, okay, let's be outside of my data. And now I don't even have the data for the outside part, but I have to use extrapolation, meaning I'm going to assume my parabola best fit is consistent even if I extend my parabola, and then sub that in and get my value. And when I do that, well, first off, the year 2012 has a value of t equals 20 because it's 2 years after 2010. So once I figure that out, I'm going to simply plug that value in. And when I do that, I should get 122 people. And I'm going to write in thousands again. Last, can this model be used to predict the number of people very far in the future? Why or why not? So parabolas in general go infinite on both sides. So meanwhile, it's highly unlikely that the lifespan would increase that way for many people. So meaning, if this is my line of best fit, if I keep continuing it and continuing it and continuing it, does it make sense for it to hit 200, right? It might plateau because in a real life scenario, maybe this parabola line of best fit isn't the best example if I try to extrapolate it way too much. So that's what I basically said in a summary. And finally, the summary is that family of functions must satisfy the given conditions in the same coordinate system, frame of reference, and answers must be exact.